Hi everyone, welcome to our lecture where we're going to go from probabilities to beliefs, and in doing that we're going to tie in a lot of the things we've seen together. Okay, so let's get started. Remember that Hume says that we cannot rationally justify a system of inductive logic. And remember, it's not just that he says that or thinks that, he provides a pretty convincing argument for it. Now, our answer in this class is going to be, well, we can't get this global justification of an inductive logic, but what we can do is give local justifications for why we should update our beliefs with probability theory. So remember that now we're going to take the subjectivist view of probability. So far, we've seen the rules of probability, but not really how to apply them to beliefs. So let's refresh our memory briefly. Remember that we want our inductive logic to help us with assigning inductive probabilities to arguments. We have a way of formally determining how we should update our beliefs given a piece of evidence, conditionalization. Remember, this is what we see in Bayes' theorem course and in the last lecture. So this says, what conditionalization says, is that if you start with the epistemic probability, which is represented by probability of H with subscript old, right? This is your belief that H. And then you're presented with a learning experience, or in other words, a new evidence, then your new probabilities should be as follows. We start at a particular time with our beliefs that H, so our old probabilities of H. You observe evidence E, that's your learning experience. And what conditionalization says is that your new probability of H, or your new belief that H is the case, should be found with the following formula. Now note that these are the hypotheses I have, right? The hypothesis is a hypothesis about probability, but they're not my beliefs about the probability. The beliefs I have are going to be assigned to these hypotheses. So let's say that I'm kind of indifferent between the two. I'm not sure. So I will assign 1/2 probability to H1 and 1/2 probability to H2. So just to make this crystal clear, right, I believe that with 1/2 probability that the bias of the coin is 1/3 heads, and with 1/2 probability that the bias of the coin is 2/3 heads. I'm not considering hypotheses where the bias of the coin is 1/2, or where the bias of the coin is 3/4, etc. Now suppose that the learning experience, which we'll represent as E1, is that the coin lands heads on toss 1. Now let's try to update our beliefs, right? Which beliefs are we talking about? Well, the beliefs in our hypotheses, so our beliefs in H1 and in H2. So the probabilities we assign to H1 and H2. Let's update these beliefs given the new evidence we've observed. So how do we do that? Right before this course, perhaps you didn't have the tools to do that, but now we do. And let's update them using conditionalization. So here I rewrote the formula, so our new probability in H1 is going to be equal to our old probability of H1 given E1. And E1, remember, is our new learning experience. We'll use Bayes' rule, which by now I hope you're confident in using, and if not, go back to the lecture on Bayes, to expand probability of H1 given E1. This is just using Bayes' rule. And now, really, we have all the material needed. We just have to plug it in, and so we get this. And now, just to make sure we're all on board here, how did I get this 1/3? Well, it's because I know what the probability of observing E1 given H1. So let's put that into words. What's the probability that the coin lands heads on the first toss, given that the hypothesis 1 is true? Right? Remember, that's what we're doing when we say given. Well, the hypothesis 1 says that the bias of the coin is 1/3 head. So here we're assuming that that hypothesis is true and try to figure out what's the probability that we would observe the evidence given that that hypothesis is true. Well, it's 1/3, right? Because the hypothesis says that the bias of the coin is 1/3 heads. How do we get this 1/2? Well, that's just our probability that you can see in the top right, our probability of H1. Right? It's our old probability of H1, which is 1/2. And lastly, we have that the probability of E1 given H2 is 2/3. Why is that? Well, remember, probability of E1 given H2 asks, what's the probability of that the coin lands heads on toss 1, given that the bias of the coin is 2/3? Well, it's 2/3. Okay, actually, we still have one more to go, which is what's the probability of H2? Well, you just look again at the top right, which is 1/2. And just with algebra, just plug this in the calculator, we have that this all adds up to 1/3. So our new probability in H1 is 1/3, right? And because the probability of H1 plus the probability of H2 is equal to 1, then our new probability of H2 is 2/3. So note that how in this last line, our probabilities have changed. When we started out, our probabilities in our two hypotheses were both 1/2, right? We didn't know which hypothesis was true. Then we observed evidence, so that allowed us to update our probabilities on these hypotheses. And our new probabilities on the hypotheses, right, in H1 became 1/3, and our probability of H2 became 2/3. Okay, so let's think about this for a second. In one of the hypotheses says that the bias of the coin is going to be geared towards tails, whereas the other one says it's going to be geared towards heads. Right? We flip the coin once, and after seeing our first piece of evidence, it lands heads. So it's natural that we're going to think, well, probably it's geared towards heads. And so this is what this shift in probabilities, going from 1/2 to 1/3, and from 1/2 to 2/3, is representing. Of course, this is just one toss, and ideally you'd be able to do this over and over and over. And this, you might think, mimics the scientific process, right? One experiment on a particular question isn't going to settle the question forever, but you might update your probability about the truth of the statement that you're concerned with. Now, if you do that over and over and over, hopefully you'll be quite confident about the statement in question. Okay, so we've reviewed a little how to calculate and update our probabilities using conditionalization, and we've just been calling these beliefs. But we haven't really given a good reason for why we should think that probabilities should be represented, that beliefs should be represented by probabilities. Well, we've actually also seen how we can judge a gamble, right? And here you might already think, well, a gamble is judged based on whether you think it's fair or not. And here already we're getting closer from gambling to beliefs. And the question that we're going to answer in this lecture is, well, how do we go from this hypothetical gambling to beliefs? And to help motivate us, here's a quote from Pierre-Simon Laplace, a really great mathematician, philosopher. I also recommend you look him up. And this quote, I think, will guide us, and I think it's nice to hear. So in one of his most famous works, he says, "The most important questions of life, which are for the most part only problems of probability." And we could even say that most of our knowledge are only known with some probability. That's what's going to motivate us. So how do we go from probability to beliefs? So let's look at an example. Suppose that Juventus and Napoli are two soccer teams, and they're playing a game of football or soccer. Now suppose that Max knows a lot about both teams. You can imagine that Max reads a lot of the newspapers, Max watches all the games of both teams, so Max is well informed. And Max believes that Juventus has a 75% chance of winning, and that Napoli has a 25% chance of winning. Right? These are the sorts of things that you might often say. Oh, I think that person might win the race, or I think I might pass the test, right? And you might even assign a particular probability to it. But what does that mean to say, well, I think that Juventus might win with a 75% chance, right? This is one game that we're talking about, one unique game. There's no other games like it, right? It will only happen once. So what does it mean that we believe that they will win with 75% chance? Well, one way to understand this, and as we've alluded to in past lectures, how we're going to operationalize this belief, is to say that if you believe that Juventus has a 75% chance of winning, that means you'd be willing to bet 75 cents on the dollar that Juventus will win. Okay, what does that mean to bet 75 cents on the dollar? Well, let's look at this diagrammatically. Again, I think it helps. So you bet 75 cents. So those 75 cents are lost. You put them in the betting pool and you've lost them. So right now you're at minus 75 cents. Now, there's two outcomes. One, which Juventus wins, right? And here you get back $1. So that's what it means to bet 75 cents on the dollar. So you lost 75 cents at the beginning with the option that if Juventus wins, you get back $1. So how much do you profit? Well, you profit 25 cents, right? You profit $1 minus what you originally put in, which was the 75 cents. But there's another outcome in which Napoli wins with 25% chance, you believe, or Max believes. Here, you get $0, right? We didn't say anything about the condition of Napoli winning, so you can assume that here you just win 0. So what are your profits? Well, since you bet 75 cents to begin with and you get 0, then you lost 75 cents, right? This is your profit or your losses. Now, is this a fair bet by Max's standards? Note here that to judge whether Max is doing something silly or not, we don't need to know anything about Juventus or Napoli. All we need to know about are what Max believes is the case, and if he's doing something silly, we could tell him. Now, is this a fair bet? Well, we need to calculate the expected value, right, of the gamble. So let's draw our table and fill it out to find the expected value of this game. So what are the possible outcomes? So note that in this case, I just told you that Juventus might win or Napoli might win. I didn't say anything about a tie, so you should assume that there's no ties here. So the two options we have are J and not J. Now, what are the probabilities of these occurring? Well, remember that he believes that Juventus will win with 0.75 probability, right? So we put 0.75, and he believes that Napoli will win with 0.25, so we just fill that in. And what's the amount won or profited? So let's just look at the diagram. So we see that if Juventus wins, the profits are $0.25, right, 25 cents. And similarly, we can look at the diagram here to see what's the amount won or profited if Juventus loses. In other words, if Napoli wins, well, it's minus 0.75, right? Minus $0.75 is equivalent to losing 75 cents. So now let's multiply for each possible outcome the probability assigned to that outcome and the amount won profited. So if Juventus wins, that is 0.1 0.1875. Just plug it in the calculator. And if they lose, then the amount won times the probability is minus 0.1875. So if you add these two together, the sum is equal to 0. And remember, a fair bet by your own standards is one in which the expected value of that gamble or of that game is 0. So is this a fair bet by Max's standards? Yes, it is, because the expected value is 0. So remember that one, but not the only strategy of justifying beliefs is by operationalizing degrees of belief with betting behavior and then to say something about that betting behavior. We're not going to say anything about that betting behavior yet, though we're going to almost get to it. But now we've seen what it means to operationalize degrees of belief with betting behavior. Because we'll say that a person believes a statement A. That's how we're operationalizing believing. They believe A with probability X. That means that they're willing to pay X dollars for a gamble that returns $1 if A and returns $0 if not A. So for example, if I believe Juventus wins with probability 0.6, under this operationalization, it means I'm willing to pay $0.6 for a bet that returns $1 if they win and $0 if they lose. Now just a few notes here. Why is it that we're saying that we're willing to pay X dollars for a gamble that returns $1 or $0? Well, that's because X is always going to be between 0 and 1 because it's a probability. Now, the second note is just to make sure that you kind of believe me in that this is intuitive, in that it makes sense that if you really believe that a statement A is going to happen, or for example, that Juventus is going to win, if you really believe that, then you should be willing to bet a little more for a little less return, right? Whereas if you really don't think they stand a chance, as is often unfortunately the case, then you should be willing to pay much less money and expect a greater reward, right? So the more you believe something, the more you should be willing to kind of bet on it, and the less you believe on it, the less you bet on it. And another note is that personal probabilities aren't revealed just by any old betting rate a person will accept. They're exposed by the person's fair betting rates. So that's why I showed you the example where with Max's probabilities, that his probabilities are represented by the fair betting rates. Now, of course, Max and anyone is going to accept, if his beliefs are operationalized as betting behavior, they're going to accept gambles or games in which it's favorable for them. But that doesn't mean that that's their beliefs, right? The person's fair betting rates exposes their beliefs. Okay, let's briefly switch gears here to think about how two kinds of games or bets might differ. So here is a first game, and I'll ask you, how do these two differ? Here's the first. You'll bet on which Olympic swimmer will win the race, but you really don't know anything about the racers nor the sport, right? That's kind of the case for me. That's one game. You really don't know anything about the sport. You might not even know the rules very well, right? How are they supposed to swim, etc. In the second game, you're told to bet on the color of the next card drawn from a deck of 52 cards. So notice that in the second game, finding the probability is kind of easy. It might require some work, or it might require you to think, well, how many colors are there in a deck of cards? How many cards are there, etc. But finding the probability, an exact probability, seems doable. Whereas in the first case, it seems much harder, right? It's much harder to assign a probability to this if you don't know anything, right? You're kind of in a form of ignorance that's quite difficult to start assigning probabilities to. And these are two different notions of probabilities, which are uncertainty, in which the probabilities are known or unknown, right? In this case, it's unknown what the probabilities of each swimmer winning are. And for example, if you don't know the rules, you might not even know the outcomes, right? So it's very hard to assign like an expected value to this game if you don't even know what the possible outcomes are. But another kind of decision under ignorance is the risk, in which you don't know what's exactly going to happen, but you know the probabilities and you know the outcomes, and so you can assign an expected value to this game. You of course won't know exactly what's going to happen, but you do know the probabilities and outcomes. So let's distinguish a little more this uncertainty with risk. Risk refers to decision-making situations under which all potential outcomes and their likelihood of occurrences, so we know all the potential outcomes and we know their probabilities, these are all known to the decision maker. Whereas decision under uncertainty refers to situations under which the outcomes and or their probabilities of occurrences are unknown to the decision maker. And so inductive logic helps us primarily make decisions under risk. It might help us with decision under uncertainty, but we won't really talk about that. We'll always assume that we know what the probabilities of the outcomes are and what the actual possible outcomes are too. Okay, having laid out all these foundations, let's briefly revisit one of our old examples from some of the previous lectures. This is a Linda example. So to refresh your memory, the prompt is as follows. Linda's 25, she just graduated college, where she was part of many social justice clubs, even on the board of one, and she partook also in many demonstrations. And the question is it more probable that Linda is A, a bank teller, or B, that she's a bank teller and active in the feminist movement? And we saw that most people think that B is more probable, but in fact A is. So just to visualize this, remember that this gray rectangle represents our space of all possibilities. And right after reading this, you might think with quite high likelihood that Linda's a feminist, right? And think that's not very likely that she's a bank teller. Now, that she's a bank teller is over here represented in blue. That's just A. And B is the intersection of A and F. Okay, so I just moved the prompt in smaller font and to the right of the screen. Now let's look at an exercise. Suppose you assign to A, which is that Linda is a bank teller, suppose you assign probability 0.10 to that. And suppose that you assign to B, which is the probability that she is a bank teller and active in the feminist movement, right, A and F. Suppose you assign to that 0.85 probability. So you believe with little likelihood that she's a bank teller, but you believe pretty strongly that she might be a bank teller and a feminist. Now note that this is a mistake, as we've seen in the previous lecture. You're believing A stronger than B, or excuse me, you're believing B stronger than A, and that's wrong, right? Because A is a weaker claim. It's much more likely for her to be a bank teller than for her to be a bank teller and a feminist. Now the question is, does this violate our probability theory? Why are we interested in this? Because we saw in the past lecture, using logic and kind of just thinking about it a little bit harder, that we're making a mistake in believing B with greater probability than A, right? But are we making a mathematical mistake here? Well, actually, yeah, you're kind of arriving at a contradiction. It does violate our probability theory, and let's see why. So the probability of A, by the law of total probability, is equal to the probability of A and F plus the probability of A and not F. And just by plugging in numbers to these probabilities, we have the following. Now, just to be extra clear, we're all on the same page. Right, the probability of A is equal to 0.1. We get that from our assumption. The probability of A and F is 0.85. Again, that's the belief we assume we're having. And just putting these two together, we get that the probability of A and not F is equal to minus 0.75. But this can't be, because the probability of A and not F cannot be less than 0. So what's going wrong here? And why is it bad, and as we'll say, why is it irrational for us to have beliefs, if they're represented by probabilities, that violate the mathematics of probability. So we'll see now. So again, suppose you assign to A the probability 0.10 and to B probability 0.85. So using the operationalization that we've seen, one way to understand this is by saying that you would bet 10 cents on the dollar that Linda is a bank teller for every dollar you get back. So note that here you don't think it's very likely for Linda to be a bank teller. So you're betting very little money, you're betting $0.10, so 10 cents, and getting $1 back. So you'd make a profit of 90 cents. So if I bet 10 cents that Linda's a bank teller, then if she actually is a bank teller, I get $1 back, so I profit 90 cents. Otherwise, I lose 10 cents. Now similarly, you'd bet 85 cents on the dollar that Linda is both a bank teller and a feminist. Now, having operationalized beliefs with betting behavior, we run into a problem. And the problem is that you're now susceptible to a bet in which by your lights you think the bet is fair, but in which you're guaranteed to lose money no matter what the facts are. Whether A holds or not, or whether B holds or not, you're just going to get what's called money pumped. And this is actually true for any probability or any beliefs that don't cohere with the mathematical theory of probabilities. And this is what we're going to see next time, and we're going to argue that if you're susceptible to such bets, that seems to be a case where you're irrational. So having your beliefs not cohere with your probabilities is irrational. Okay, so in sum, and how to operationalize beliefs with betting behavior. In the next class, we'll see why our beliefs should cohere with probability. And I already gave you a little snippet of it, which is because otherwise we're susceptible to really bad bets by our own standards. Thanks. Looking forward to next class.